width is that, because that's an image which is taken with a group of telescopes, very complicated, but if you are close, that's what we are going to see. In fact, we're going to see, the way to interpret this is that this is a ring, a red ring, badly out of focus. When we go there, we're going to see the same, but much more sharply in focus. There's going to be a clearly defined red ring. Now, let me tell you why we're going to see that. First of all, it's not that around the hole there is just a ring of things, because if there was a ring, we would see like the ring of Saturn's. We would see sometimes just like that, sometimes just a line, okay? No, black holes, you see the ring from whatever direction you look at it. You always see a ring. Why? Because this ring is not a thing. This ring, it's a optical phenomenon. It's like a rainbow. It's completely an optical phenomenon. And it's not the light of the black hole. It's the light of a lot of stuff around it, but which is all over around it. And the reason we say a ring, it's the following. One of the consequences of Einstein's theory is that not only masses are attracted by gravity, but also energy. You know, Einstein E is mc squared, so whatever energy does, mass does, whatever mass does, energy does. So mass falls, energy also falls. And so light has no mass, but has energy, so also falls. So it's attracted by the black hole. And it's also attracted by the sun. But the sun, it's very big, given the mass. So even if some light comes very close, it's attracted a little bit, deviates a little bit. In fact, this was measuring that was one of the first evidence that Einstein was right. But a black hole is very, very massive. So given the mass, it's very small. So when the light comes very close, it's attracted a lot. So much that you can do a simple calculation. It's done in all classes of GR. And light can be in orbit around a black hole. So you can flash some light and just goes in orbit. This orbit is at some given distance from the black hole, fixed distance from the black hole, sort of 1.5, 3 times its radius, something like that. 1.5 times its radius, something like that. And so this means that light can go around this way. Now, careful. Imagine this is a black hole, and here there is something shining, some hot matter shining. Then you see it because light comes to you, but you also see it because light curves a lot and goes to you. But you also see it because light makes 2 turns and comes to you, or 3 turns and comes to you. So you see it multiple times, once here, but all the other times you see it here. And the one is here, you see it here. And the one is here, you see it here. So you see everything many times, and many times just from this distance. So you see a ring, a clear ring. And of course, if you look from another direction, the same. You see a ring like that. So that's a ring. And the beautiful part is that, you know, I study that in my textbooks, in the one that says, yes, but this doesn't happen. Here it is, it happened. So we go there, and we see this ring, fantastic, we're very happy. Now we go closer. We go closer to a black hole, starship. Imagine this is a much bigger black hole, so this is a small starship. We go close. If we let us go, we fall into it, but let's keep the rockets on, so let's keep at a distance. And the second phenomenon I want to describe is a time dilation, just maybe the most spectacular at all. The following happens. So we stay at some distance from the black hole. We come a little bit closer, we stay at some distance, closer, and so on. And imagine we had the news from Earth. Earth was, your daily news. Every 24 hours, you listen to, I don't know, CNN, Fox News, Al Jazeera, whatever, I mean, TASS, China Daily, whatever. Now, as we get closer, we get the news, not every 24 hours, but every 10 hours, 5 hours, 3 hours. And when we're very close, we get one news very fast, one other. So if we look back at Earth, we see everything happening very fast. And if we are on Earth, and somebody gets messages from us. We send messages once a day. Back on Earth, they receive it every 2 days, every 5 days, every week, every year, the more we get close to it. That's time dilation. So time dilation is not something that we see here. On the starship, I mean, there's a weight, the attraction, but time is normal. We just wake up in the morning, and get breakfast, everything is normal. Clocks go at the same time for us. But we see everything far away going fast, and people see us going slower. So time goes slower near a black hole than far away. This is a phenomenon that we measure in the laboratory, but near a black hole becomes colossal. The more close we get to the black hole, the more we are seen from Earth slowing down. When we cross the black hole, now we go in. From Earth, they don't see us anymore. They see us just at the last moment before entering. Okay? And now we're in, going in. Now, when we cross it, you may say, oh, now we're crossing this boundary. What happened? Nothing. Okay? In our starship, everything is completely normal. Just cross, outside, inside. We cannot go out anymore, but once we are crossing, in the starship, everything is normal. And that's why it's called horizon, right? It's called horizon because it's the same thing as the horizon of the sea. If you go on a hill and look at the ocean, you see a line, and the ship going behind the line disappears. But it's not that there is a line on the ocean, says here is the horizon. I mean, when you're on the boat, the ocean is completely normal. So the line is this surface, is the line we cannot see beyond, like the horizon. Why? Because space-time is curved, like the Earth is curved, so you cannot see behind. We're inside. Now we're inside the black hole. We still see the stars around. We can still get message from Earth. Okay, they cannot be our message, but we still see message, assuming that Earth is not in the future for us. So assuming humankind still exists, but we're still there. We go in. Everything is locally normal. But if we look a little bit around us, funny things happen. And this is the third effect I want to describe, which is space deformation. And let me describe it in this way. If I ask you to guess what is inside, it's just air compressed because this is it's full. But if I ask you what is the volume, how much is the volume inside, well, this is roughly a foot.